spend some time on the dynamic analysis. Okay, so let me upload the file to the tree. Okay, this part is mainly to kind of help you to later do the analysis of your job test. Okay, we will not spend time doing the numerical analysis, but after you obtain the stiffness of the structure, then you're going to calculate what we call this part is for you to kind of have a basis about the talk test. We will only cover some basic, and then you later go and try them out. Okay. So this is the form, then you can put up, and you'll see the, let's say, okay, so as you can see, just now there are some
认为是保健宠物或上虾皮，贝洁雅卫生纸单抽不到1块钱。
Okay, for our
We previously posted a video of Go One.
for our this previous analysis, we were mainly concerned about the suspension of the dog-like leg. Okay, so we concern is used for landing, but in reality, you can see this more commonly for locomotion.
Struggling to get up, stair evaluating, shift to, or go to doing the same action. So you can see Go One here just struggling to get up to this first step. It finally does, and then
So this is
second
some
step,
example that it is
8
used
inches
for
tall, and it is
uneven
unable to
terrain.
do so.
Yeah.
Go to shifts from the factor to 2 separate stair climbing modes. Mode 1 is similar to Go One's capability.
Yeah, so this is the development for the robotics, but if you look closer, yeah, you have to go for this
Stair climb.
Let's check out Go 1's stair climbing abilities. On the remote controller, we can use any button on the left-hand directional pad in conjunction with A, which puts Go 1 into stair climbing mode. You'll notice the gait of Go 1 has changed, where it begins walking in a sort of high step mode. Use the directional controls as usual when navigating to the steps when within stair climbing mode. You will need to be in stair climbing mode to go up or
好，然后回过头来，我们来看一下这个掉落实验。Okay, let's come back. So for this robotic dog or robotic humanoid, you can see that they rely on the footstep for locomotions. But one of the issue with leg locomotions is for every step, this is a drop test. Okay, so the landing of the leg, okay, so far is well controlled by animals, but not so well controlled by robots. Okay, so especially for humanoid with the two legs. Okay, for every step they come down is a drop test. Okay, so the drop test not just happen to, we'll see the example rather than the formula. Okay, let me show you the example. Oh, okay, so this is a short one. Okay, let's see. Let's go to the vibration lecture on test. Okay, we'll see the everyday drop test. So landing itself is a drop. So this is showing you the fighter jet going to land. Okay, we'll show you the fighter jet going to land. One on the runway, the other on the aircraft carrier. Landing, okay, is challenging. Why? Because upon landing, your speed of the aircraft is going to decrease. So at a high speed, you have lift to overcome the weight. But when it comes to land, the speed will decrease, and lift is not enough to cover the weight. As a result, then there will be a sudden drop. Okay, so this is what we call a drop test. So for aircraft, for your smartphone, or for your rocket, if you need a lander, let's see how you get. Traveling. So this is on the aircraft carrier. The fighter jet is coming to land. They're going to pitch onto the So you can see that when it's coming to land in such a short runway, okay, so it may have a chance of losing the speed, and then it's coming to land roughly. Let's see what the aircraft design has to be. Okay, for example, A18. Okay, wait a second. So this is the aircraft under the drop test. So with the lander, okay, you can see the length of the aircraft. Let's play it again. Okay, I think it's too fast to see. Then let's see the slow motion. So you can see the aircraft landing with the wheel turning. Yeah, and then the leg must be bendable so that you can increase the shock. Okay. And then likewise, yeah, you can also see the landing of the many larger aircraft. So this got 4 sets of landing gear and wheels. Okay. So when you land on the runway, okay. It is a real wheel landing force and then I think it's just able to direct during the day. Yeah, some aircraft, I think aircraft from Xinyu come to land, okay, but they have a hard landing rather than soft landing. Okay, so but is it the issue to the lander? So let's view the requirement of the lander for aircraft, especially the passenger aircraft. This is the one for Airbus A380s. Okay. So they have to simulate the lander landing situation. So they have one set of the landing gear, okay, to be dropped from a height. For this landing gear, they basically have 3 pair of wheels. Okay, to make the wheel turning, they have a driver wheel. Okay. Okay. So this landing is crucial to the passenger safety as well as the comfort. Okay, just a cushion on your chair. Okay, you can see this test rig. Yeah. So they are going to drive these 3 pair of wheels into the running speed well above the ground, and then they finally let go. Okay. And then they release these landing gear from the height. Okay. The importance of the landing is, yeah, it must cushion the shock. So this test site is happened to in Canada. I think the Airbus have contracted the test center in Canada to do this test of their Airbus A380s landing gear, one of the largest aircraft ever sold. Okay, but one of the issue with this aircraft is it's too heavy. Okay, you need more than 1 set of the landing gear. You can see that one of the important part about this landing is you must have some spring, either coming from the wheel or either coming from the suspension to absorb the shock. The spring in the wheel is too high because the wheel is to support the weight. Okay, not enough. Okay, so for this part, then I'm going to tell you. Okay, for this kind of landing, how do you model it? Okay, you model it as a mass. You model it as a spring. Mass is for the mass of the aircraft. Spring is the spring coming from the wheel or coming from the suspensions that come into the stand, the contact with the ground. When it's coming down at the height, it's going to be free falling, descending in the height and gaining in the speed. And then this is the impact speed V naught. You can calculate the V naught as the square root of 2gh. Okay? And then you can focus. In the end, there are no force acting on the mass and the spring. So what you did calculate in the previous ANSYS and experiment is the stiffness, is the diffraction. So this is all static. Okay? But when it comes to shock, it is a sudden landing. This is going to be the step force applied. This force appears to come from the ground reaction force coming from the weight. And then the spring, which is the landing gear, is to be compressed. Okay? So then your equation of motion is Fx double dot Kx equal to mg. So what did you do with the structural analysis previously? You are talking about Kx equal to mg. Okay? But for the landing, the accelerations have to come to the equation. It can be quite complex. But for us, we're going to do semi-analytically. You still do your structural analysis to estimate the stiffness. Okay? But you're going to use the analytical formula to predict how much is your accelerations upon contact with the ground. Upon contact with the ground, your suspensions or your spring is unloaded. Okay? But at this point, it has a starting speed, which is the square root of 2gh. I think this matter is very troublesome. Okay, so there's starting conditions. And what's the answer? Your answer is, because this ordinary differential equation is second order ordinary differential equation, the answer is A cosine plus B sine. Okay? And the extra weight applied to the spring has a static non-homogeneous solution with this M0 here. Okay? So in this case, what's the answer? Your answer, when it is not loaded, it is A cosine plus B sine. We will find the amplitude A and B by substituting the initial condition. And then for the non-homogeneous solutions, you simply can assume polynomial function of time. And eventually you find the answer. Okay? And this answer is mg over k. That's it. So by combining the free vibrations plus force vibrations, you have the answer for displacement. At time 0, displacement is 0. That's why you find the answer A is equal to minus mg over k. And then next, how about the initial velocity? At time 0, the velocity is square root of 2gh. So you find your B is square root of 2gh divided by omega n. Okay? So with this, apply and combine, then you'll be able to find out what is the amount of the acceleration. And this amount of the acceleration, if you go and obtain, it is this g times the square root of k over n times 2h over g plus k. So meaning, when you are following something, like for example, this eraser, okay, for the blackboard. Okay, if fall with the sponge there, okay, you can hear the sound. The landing will be softer. 有没有听到？那个声音比较强。那你如果反过来用它背着地，用它高一点。OK， 所以这个声音就差很远。OK， 所以这就是掉落实验的结果。所以后面你们设计你们的这个手机这个起落架 ，OK， 所以你就要去选择，我的弹簧到底要多硬多软，我们要求是从多高丢下来，经理，我们要求多高？0.1米丢下来的可能多高？手机大概1寸晶圆，不4寸晶圆的直径掉下来 ，OK 啦。为了你手机的安全，100 mm 够了 ，OK。然后最后期末的这个分数啊，我们就按你的冲击力的大小 ，OK。用你手机计算，那你手机每个人手机都有加速度规 ，OK， 你如果装一个 Firefox， 这个软件 ，OK， 你开始在摔手机，它就开始记录你的加速度 ，OK， 看到没有？读书都有，你怎么蹦蹦跳跳 ，OK， 所以你手机可以记你一天走多少步，你知道手机怎么？记你生活健不健康，一天能走1万步 ，OK， 手机有这个功能啊，对不对？为什么它知道你每一步 ，OK， 而不是挥动，因为你每一步都是掉落实验，冲击力最大的时候，不是你的手左摇右摆能产生的加速度，你每一步下去，手机都觉得很钝 ，OK。所以你们这次那个期末前的 NCS 的这个 project assignment 就是要弄一个起落架，你的手机大概这个100 mm 的高度掉下来 ，OK， 然后看看谁的这个减震比较厉害。Yeah, so that's the background. Okay, and coming back to the model. Okay. So here I don't care much about what is exactly you did, okay? But can you use your MCs to help me calculate what's the equivalent stiffness? Okay, because actual structure could be very complex. Let's get the first